Hi everyone, my name is Jennifer Karpuk, and on behalf of me and my peers, I want to thank you for coming to view our Introduction to Cross-Laminated Timber for Dr. Alam's Engineering 325 class at UBC Okanagan. Before we begin, I'll give you a quick overview of what's to come in this presentation. First, we'll take a look at the composition of CLT. Then Avery will go into the building applications. Brett will discuss seismic and fire resistance. And then Ryan will give a prediction for future trends of CLT, including tall building design. CLT is a relatively new civil engineering material, but is quickly gaining popularity for a number of reasons. This is due to factors like increased fire resistance, minimal waste, and its ease of use. CLT is typically characterized by 3 layers of alternating, interlocked planes of dried spruce boards that are epoxied together. In Figure 1, you can see how the narrow faces alternate between layers, and then along here, the longer edges are joined together by finger joints, which are primarily used to take the vertical and horizontal loads and then apply them to a single element, thereby lessening the stress concentration. After being planed, these layers are then epoxied together by a polyurethane or a melamine urea formaldehyde. The polyurethane is more common due to its ability to control thickness and curing time, but the melamine urea formaldehyde offers better gap-filling properties. The fact that CLT is pre-manufactured means more control of its properties in comparison to natural timber, but also quicker and easier installation, which can often rival precast concrete. To speak on CLT's building applications, I'll now pass this over to Avery.
CLT is used as long spans in roofs, floors, and walls. To reduce construction time, these members are prefabricated off-site and inserted with the use of heavy equipment. Walls and roof spans of CLT are often left exposed in the inside of a building to add visual appeal, showing off its cured epoxy finish. CLT is becoming widely used in residential and office buildings in many countries. CLT can be used as a replacement to lightwood framing. Time is considerably decreased when walls can be put up as massive pieces versus being built piece by piece on site. This convenience is particularly useful in large-scale buildings. For example, the UBC Vancouver campus's Brock Commons building is 18 stories high. Using CLT members, the building structure was completed in 70 days. It was estimated that without CLT, it would have taken over 4 months. CLT makes use of timber, which has low carbon emission life cycle. Using CLT could reduce the predicted 70,000 tons of CO2 emissions by nearly 22%. This is an important consideration because cities such as Copenhagen, Denmark, are aiming to become CO2 neutral. I would like to pass it off to Brett, who will be talking about fire resistance.
Thank you, Avery. I will discuss both the fire resistance as well as the seismic behavior of CLT. For the fire resistance, I will begin with a general overview of the behavior of CLT during burning, and I will go on to discuss a case study regarding this topic. The burning of CLT begins with the charring of the initial layer of timber. The charred layer eventually falls off, which releases energy and reduces the cross-sectional area of the panel. The charred layer provides protection for the underlying layer to increase the duration of time until failure. The falling of the charred layer is affected by many factors. For example, the thickness of each layer of timber, the use of the panel, and the temperature of the adhesive. The reduced cross-sectional area, along with a constant load, increases the stress on the member, which could ultimately cause it to yield or fracture depending on the severity of the burn. The group also researched a case study performed by Schmid, among others, on the burning of a CLT member. A CLT member was placed on a roller and hinge support 1,500 millimeters apart, and the fibers of the panel were placed in the same direction of the load. The member was then exposed to the fire, and it behaved similarly to the pattern described previously. As you can see from the picture provided, the outer layer on the edge of the panel is charred. This photo was taken after the researchers performed a fire test on the member. These tests emphasized on the zero-strength layer, which is an additional layer of CLT added to the charred layer, which allows researchers to decrease the variability when considering losses in stiffness and strength. The zero-strength layer leads to conservative designs, which will eventually become obsolete with new advances in the field. The researchers ultimately found that CLT failed when the thickness of the load-bearing layer reduces to a few millimeters during burning. For the seismic behavior, I will touch briefly on CLT behavior during natural disasters, the SOFI project, high-rise buildings, as well as the current seismic design. The world is starting to see more powerful storms, and designing for increased seismic protection is becoming necessary. Due to CLT being a relatively new material, especially in North America, there have not been many tests on the seismic behavior of CLT structures. This area of research is a must, as there seems to be an increase in CLT popularity. A major test that the group studied was the SOFI project. This project was done with the Earth Science and Disaster Prevention Unit in Japan. The tests were completed in Italy and consisted of shaking, pseudodynamic, and in-plane cycle tests on various dimensions and heights of buildings. The test found that CLT is a suitable material to use when building in high seismic zones. For example, full-scale shaking tests up to a 7-story building were found to be non-destructive. Current CLT designs have mechanical connectors that connect the wall and floor, which proved to be very stiff during quasi-static tests. As of right now, CLT is only safe for mid-rise buildings if they are built in moderate to high earthquake regions. There have been some studies that are looking into the potential of altering some stories to be rigid to achieve ductile behavior. This would allow these stories to stay intact during seismic events. This can be achieved by having some stories have increased ductility to act as a sacrifice of sorts. The long rigid wall panels are segmented into shorter wall panels with brackets at the corners of each of them, which allowed the designs to achieve this measure. Thank you for your time. I will now pass it off to Ryan to discuss the future trends of CLT.
Construction with CLT is rapidly becoming more popular and also rapidly more regulated and specified. Various grades of wood, types of glue, and additives are also being researched to improve the current properties of the material. Strict standards are set in the construction and implementation of CLT in buildings. There are specific parameters that are set in each country or region that govern the size, strength, and usage of CLT members. This ensures consistency in the members as well as ensures the strength specifications for each particular member are met. In 2009, the Canadian Building Code was amended to allow wood frame buildings to be constructed to a height of up to 6 stories. This assumes they are built following the rest of the specifications in the code. Newer technologies and methods of construction such as CLT have been a driving force behind much of the research that had been done and have backed the changes to the code. A previous restriction for tall timber frames buildings is fire resistance. But as talked about previously, CLT members, when used in conjunction with other fireproofing methods such as sprinklers, have a good fire resistance rating and is therefore a viable material to use for such buildings. Due to its green rating, as well as its reliability and consistency, CLT implementation is increasing throughout the construction industry across the globe. Currently, the base cost to construct a timber frame building is roughly 10 to 20% higher than the cost of an equivalent reinforced concrete building. These costs are easily made up during the construction phase due to the simplicity that comes with the erection of prefabricated members. The ease of installation, along with workers being familiar with wood building materials and on-site errors being quickly and easily mended, means less man-hours and quicker construction. As continuing environmental restrictions are imposed on construction, as well as clients wanting greener ratings on their buildings, the use of CLT in tall buildings is becoming of increasing interest. The consistency of the strength of the members is also key to this implementation as they are equivalent to other building materials, but easier to install and greener. As such, a 10-story apartment building has been constructed in Australia, and another similar structure called the Stout House was built in London, taking 9 weeks and only 4 workers to complete, thus showcasing CLT's efficiency and capability. Continued research following the construction of Stout House has been done, and when using proper design techniques and in joining elements, it is estimated that the heights achievable by CLT panel buildings can be pushed to 25 stories, or even higher than that when using a hybrid of CLT members and a concrete core. And now I'll pass it along to Brett to conclude the presentation.
Thank you, Ryan. Our project touched on building infrastructure with CLT, fire resistance, seismic behavior, and future trends of CLT. Although CLT is a relatively new material, the group believes it will transition into a popular choice for building infrastructure. On behalf of Avery Bridge, Jake Borsboom, Jennifer Karpuk, Ryan Sahlstrom, and myself, we would like to thank you for taking the time to listen to our presentation, and if you have any questions, we would be happy to answer them. Thank you.